Now what we're going to look at is a deep neural network where you have a collection of these sigmoid neurons. So before we move on, right, you have to understand this, that every neuron has the following input-output behavior, right? You have an input x, where x could be a m-dimensional vector, right? Each of these x's gets multiplied by a weight, so you have this summation wi xi. Then you have a bias, so you have summation wi xi plus bias. And then you take the sigmoid of this, which is 1 over 1 plus e raised to minus summation wi xi plus b. So every neuron, this is how the input and output behaves, right? So a more compact way of writing that is the following. So this is your neuron, this is the output y, and you have several inputs x. So you have x1, x2, up to xm, and you have the corresponding weights also up to wm, right? And then you have one bias. Okay? So the way, if I want to write the output as a function of the input, then the way I write it is y is equal to sigmoid of summation I wi xi plus b, right? So I equal to 1 to m. Okay? And when I say sigmoid of anything inside the bracket, it basically means 1 over 1 plus e raised to minus that quantity which is inside the bracket. So in this case, it would be, instead of z, you will have this quantity which is there inside the bracket. Now, there's one compact way of writing this. Can you tell me what it is? If I think of w and x as vectors, w transpose x, right? So this is going to be w transpose x. Is everyone fine with that? Please raise your hands if you're fine with this. Okay. Fine. So just remember this, that we can write for any given neuron, we can write y is equal to sigmoid of w transpose x plus b. Is that fine? Okay, everyone gets this? Okay. So with that background and quick recap, we'll just move on to deep neural networks. Okay. So again, here's the setup. The input of the network is again going to be an n-dimensional vector. So these n-dimensional vectors, basically the n features that you're considering for the problem at hand. So this could be salinity, pressure, density, and so on for the oil mining case. Right? Then the network has a total of L minus 1 hidden layers. Okay? So let's see what a hidden layer is. So this is what a hidden layer looks like. So what will happen is, if I consider any of these neurons here, let's focus on the first blue neuron in the first row, right? So in the first blue row, let's focus on the first neuron. So that is going to take inputs from all the red guys, right? All the red inputs are going to feed to that. It's going to take a weighted sum of these inputs, add a bias, and then compute the sigmoid. Everyone gets that? That's exactly what I showed on the rough work, right? So each of these neurons, right? So this, consider this to be one of the blue neurons that you have, and these are all the red inputs that you have. So each of these blue guys is going to execute the following function, and the weights are going to be different for each of these blue guys. Does that make sense? Okay, fine. And then finally, you have an output layer. So suppose you're dealing with a classification problem, right? So far we have been dealing with binary classification problems. I want to know whether I like it or not like it, or whether someone will commit a fraud or not commit a fraud. But you could also have multi-class classification problems, right? So where, suppose you're given an image and you want to decide whether this is an apple or an orange or a banana or a mango or so on, right? So there could be many classes, as many classes as the number of fruits that you have in your data set, right? So then, in general, we'll have k classes. So far, we have been dealing with a case where k is equal to 2, right? We just had 2 classes, okay? So now each neuron in the hidden layer and the output layer, we're going to split it into 2 parts. Okay? So let's see what these 2 parts are. The lower part is called the pre-activation, and the higher part is called the activation. Okay? So the lower guys, I'm going to refer to them as AIs, and the upper guys, I'm going to refer to them as HIs. Is that fine? Okay? So you have 2 hidden layers. So you have A1 and A2, and H1 and H2. Okay? Now, what is this business of splitting it into half, right? What does the lower half do, and what does the upper half do? So the lower half, so we'll come to that actually, so I'll just come to that. And the input layer can be called the 0th layer. So you have layer 0 as the input, layer 1 and 2 in this case as the hidden layers, and layer 3 as the output layer. Okay, so that is total of L equal to 3 layers, L minus 1 is equal to 2 hidden layers and 1 input layer. Okay, so this is a typical deep neural network. You can call it a feed-forward neural network or a multi-layer perceptron or a multi-layer network of perceptrons. All these are equivalent terms, right? And this is what it will have. It will have an input layer, a few output hidden layers, and then 1 output layer. Okay. Now let's look at some things. Now every input is going to be connected to every neuron in the first hidden layer. Is that fine? Okay. So now if there are n inputs and n neurons in the hidden layer, how many weights will you have? Forget about weights. How many edges will you have? If I have to connect every guy in the input layer to every neuron in the hidden layer, how many edges will you have? How many? N square, right? Each of the n guys connected to each of the n guys. So then how many weights will you have? N square, okay? And if I put them into a matrix, then what would be the dimension of that matrix? N cross n. And then you also have biases. How many biases will you have? No, one for each neuron, right? So then you'll have n biases, okay? So let's look at that. So you have this weight matrix W1, which is of dimension n cross n. Then you have the bias, which is of dimension n, right? And what about the next layer for W2? Again, I had assumed that there are n neurons in every layer. So each of these blue n neurons in the first layer is going to be connected to each of the blue neurons in the second layer. So how many weights will I have again? N square, which is again in a matrix n cross n. And then there will be a bias for each of the blue neurons in the second layer. So how many biases will we have? N. Now, again, each of these blue neurons in the second layer is going to be connected to each of the green neurons in the third layer or in the output layer. How many neurons are there in the output layer? No. How many neurons are there in the output layer? K, right? If we have K classes, we have K neurons. Is that fine? Okay. So now how many weights will be there in the output layer? N times K. What was the dimension of that matrix be? N cross K. And what would be the dimension of the bias vector be? K. Good, right? So that's how this is going to be, right? So this is, so I've told you all the neurons. I've told you all the parameters of this model. Okay? Is that fine? Okay. Now I've not told you how to compute these HIs and AIs. What I've given you is just a schematic. I've just given you a diagram, but I've not told you how these W's and X's and B's interact with each other to finally give you the output. Okay, so let's look at that. So each of these AIs is actually given by the following formula, BI plus WI into HI minus 1. What does that mean? So let's look at that, right? So what I'm saying is, let's consider a very simple case where you have 3 input neurons. You have X1, X2, X3. And in the first hidden layer, which I'm going to call as H1, okay, you have again 3 neurons. So each of these guys, I'll call them as H11, H12, H13. Is that fine? Okay. Now what's the dimension of the weight matrix here? 3 cross 3. Okay. Is that fine? So what I want is, or actually I'll just look at the AIs first, right? So I'll call them as A11, A12, and A13. So the lower half. The lower half is the A's and the upper half is the H's. Is that fine? Okay. So I want to find, so what I had on the previous slide is a formula for AI. So I had said that AI is equal to BI plus WI into HI minus 1. What is the value of I in this example? What's I in this case? 1, right? So what I'm saying is A1 is equal to B1 plus W1 into H0. What is H0? The input layer. Is that fine? Everyone gets that? Okay. So basically I'm saying W1 into H0. Okay. And H0 is the input layer. This is the same as X. Okay. So let's do that also. So this vector is actually X. Is everyone fine with that? Okay. And what is this vector? Can you tell me what is this vector? A1, right? It's just a collection of all the elements in A1. A1 has how many elements? 3. So A11, A12, A13. So just a collection of them is A1. Is that okay? Fine? Okay. So what is this equation actually telling you is the following. Instead of H0, I'll just call it X, right? Is that fine? Everyone okay with this? Now what are the entries in the matrix? Can you tell me? This is the W1 matrix. What are the entries in this matrix? W1, 1. So 1 is for the matrix, right? This is W1. Similarly, we'll have W2 here, right? Or let me just simplify things. I'll just put W1 as the superscript, okay? So now can you tell me what are the elements here? This is W1, 1, 1, W1, 1, 2, W1, 1, 3. Is that fine? Okay? Fine. So now given this product that I have written, can you tell me what A11 is going to be? Anyone has a difficulty with this? If I write it as the following, will you be fine with it? Right? And similarly, you can write the formula for A12, A13, and the whole thing, if I want, so I have given you a formula for A12, A13, okay, which is going to be similar. We'll have B2 plus the appropriate sum. This whole thing, can I write it as a single matrix operation? So what do I have? I have a vector is equal to a vector plus a matrix into a vector. Is that fine? So can I write the whole thing as A is equal to B plus W into X? Okay? And in general, A1, so in this case it was A1 is equal to B1 plus W1 into H1 minus 1, right? So that's H0. Is everyone fine with this? So what's the general formula if I replace it by I, 1 by I? AI is equal to, I want everyone to say this, BI plus WI 1. Is that fine? Okay. And now on the slides, I'm going to just move that I to the bottom, right? So I'll have WI instead of W superscript. Does everyone get this? Okay. So this is the same thing. You have just aggregated a weighted sum of all the inputs, but for the entire layer, you can write it as a single matrix vector operation. Instead of having these multiple equations, you can just write it as a single matrix vector operation. How many of you get this completely? Please raise your hands. Okay, good. So that's what this equation is saying, right? For any generic AI, is it going to be BI plus WI into HI minus 1? Okay. And the x's that you have in the bracket, they're just saying that AI is a function of x, right? So AI of x, that's all. This one? Yeah. So I already given you the first row. The second row is going to be 2, 1, 1, 2, 2, 2, 2, 3, 3, 2, 3, sorry, and 3, 1, 3, 2, 3, 3. So let me just tell you what, say for example, W1, 2, 1 is, right? So it's the weight connecting the second neuron in the hidden layer to the first neuron in the input layer. So the indexing is a bit reverse, right? Output first and input later. So when I say 2, 1, it means second in the output layer, which is the hidden layer, and first in the input layer. Is that fine? Everyone okay with this? Okay. Okay. And now what is HI going to be? So far what have I done? Weighted sum of the inputs. Now what does the sigmoid neuron actually output? What does it output? Sigmoid of this weighted sum, right? So what do we get is sigmoid of B1 plus summation I equal to 1 to 3 W1 1I xi, right? This is what the sigmoid function outputs. Okay, so this was the aggregation part which the lower half of the neuron has done. Now once you have this aggregation, the upper half is just going to apply the non-linearity on top of that. The non-linearity is the sigmoid function in this case. Everyone fine with that? How we have divided these two parts? The lower part is just doing the aggregation, and the upper part is now going to apply the sigmoid on top of that. Is that okay? So G, I'm just calling G as a generic sigmoid function. Okay, it could be the logistic function or the tan H function or any other function from the sigmoid family. Is that okay? Fine. And finally, the output. So you have computed this, the lower green layer. The lower green layer is going to be again what? How do you compute the lower green layer, the light green layer? It's again a weighted sum of the inputs. It's going to be the same. So it's going to be given by the same formula as on the first equation on this slide, right? But now once you have this, you want to generate some output from that. So that output function, I'm going to call it as O. Okay, I'm just going to call it generically as O, and we'll see what is the right output function to choose depending on the tasks that you have. Okay, so for right now, just let's call it O. And now I'm going to simplify the notation. So instead of these x's in the bracket, just notice on all these things you have the x in the bracket, which just tells you that this is a function of x, but we all know that already. So I'm just going to remove those and just simplify it as ai, hi, and so on. I'm not going to write ai of x, hi of x, and so on. Everyone find this? Okay. So everyone completely understands how do you go from the input layer to all the way up to the output layer? How many of you are not clear with this? If you're not clear with this, you'll not understand the rest of the 2 hours. I don't mind repeating it. Which one? Output? This one? So the lower half is the lower green, light green part. So that is again going to take a weighted sum of all the inputs to it. And what are the inputs to it? The hidden layer before it, right? So that's again going to be given by this formula that you see at the top. Okay. Now once I have that, I need to produce an output from there. So I'll use some output function. Just as there's a sigmoid function, I'll use an output function which gives that output. Now what output function to use, I have not told you that. And that will depend on the task that we have, and we'll come to that. Okay, but what you need to do is, again, there the light green part is going to take an aggregate, and then from there I'll have to produce some output. How to do that, we'll see. Okay, so now I have written this output. At the output you have a y, or rather y hat. Why do I call it y hat and not y? It's r. It's a predicted value. It's our approximation of the relation between y and x. It's not the true relation between y and x. We don't know what the true relation is. Okay? And I have written y hat as a function of x. Okay? So now, here's the thing now, right? So yesterday I started off with this thing that in a supervised machine learning setup, you have this setup where you have the input x's and you have the outputs y. And then you had these 5 elements. What were those 5 elements? No one looked at the slides after going back? Data, model, parameters, objective function, and learning algorithm. Okay. Where is all that here? What was the model yesterday? What was the model that we were working with? Y is equal to, what was the model yesterday? Sigmoid of x. Our approximation was that I don't know how people take decisions to watch movies, but I believe that they take it in the following manner. They compute y is equal to sigmoid of w transpose x, right? And now I'm going to learn w's so that my predictions are as close to the predictions given in the training data or the real outcomes given in the training data. That was my model. I could write it down as an equation. But now here all I have is a diagram. How do I write this as an equation? I want to be able to write y as a clear function of x such that there are certain parameters in it, and then I can learn those parameters using some objective function. So how do you write y as a function of x in this case? Is y really a function of x? Yes? What kind of function is it? Can you write down that function? Can you actually write down this function? Because I could write y is equal to sigmoid of x, right? I could even expand it as y is equal to 1 over 1 plus e raised to minus w transpose x, right? That was very neat. I could write it exactly. And then I knew that w are the parameters that I need to learn. Now here, if I can't even write the equation, then the question of learning the parameters and all is secondary, right? How do I write the equation? Because only when I write the equation, I'll understand what are the parameters and then come up with an objective function and do something on top of that, right? So what are the parameters here? What is the equation here? How do you write y as a function of x? Try. You have dealt with functions like y is equal to sine of, cos of, tan of, e raised to x. Right? What kind of functions are these? These are composite functions. Right? You take an x, you do a lot of transformations on that, and then finally arrive at a y. Are you doing something similar here? Yes? Then can you write it? Once I write it, and I'm going to write it, it will be plain obvious to you. Right? You're like, oh, this is so simple. Why was he even asking this? Right? But when I ask you to write it, you'll have this mental block that you'll not be able to write it. So why that gap? Just try it. But what is HI? I think you get the gist of it, but you're not quite there. You have to expand it, right? So for example, right? Suppose it's sine of, cos of, tan of, e raised to x. This part of cos of tan of e raised to x, I can just write it as z. And then I can say y is equal to sine of z, where z equal to something. And then inside that, again, you could do these simplifications, right? Then what you have told me is that y is equal to sine of z. I'm asking you what is z now. Do you get that roughly? Yeah. Okay, it's not very difficult. I'll just do it because there's not enough time. So let's look at whether this problem itself, now when we have used a neural network, do those 5 elements still hold? Can I still have data, model, parameters, learning algorithm, and objective function? Right? That's what I want to see. The data is fine. Suppose this is a credit card fraud detection thing, or let's say this is a multi-class classification problem, right? So now suppose I want to decide whether the given image is an apple or a banana or a mango or a watermelon, right? Suppose this is what I want to decide. So what is my input there? I've suppose given you a 30 cross 30 image. What's the input? The pixel values, right? So the 900 pixel values are my inputs. So my input is 900 dimensional, and the 900 pixel values are my inputs. And what's the output? How many layers, how many neurons are there in the output layer? 4. There were 4 classes, right? So 4 classes maybe. I said 3 maybe, but 4 classes, okay? So apple, banana, mango, and watermelon. So there are 4 classes. So your input has 900 pixels and your output has 4 classes. And in between you have certain number of hidden layers, right? So your x and y is clear. X is raw pixels, 900 pixels. So x is 900 dimensional and y is 4 dimensional, okay? Now what's the model? And this is the model which I have chosen. So what's the model? And that's exactly the equation I was asking you. And the model is actually the following. So let's start from the innermost bracket. I took the x, I did a transformation of that. I did w1x plus b1. Then I took the sigmoid of that, so that's the g function. Whatever output I got, I again did a transformation of that. I did w2 plus b2. Is that fine? Whatever output I got, I applied the sigmoid function to that. Again did a transformation of that. So I did w3 into that value plus b3, and then finally applied the output function to this. How many of you get this? Please raise your hands. How many of you did not get this? Please raise your hands. You did not get this? Or many of you did not get this. Okay. So focus on the innermost bracket where you have w1 x plus b1. So what is x? X is your input. Okay. The first thing that you did is you did this weighted sum of the inputs, which is nothing but this simple matrix operation where you have w1 x plus b1. Everyone fine at this point? Once you got that output, what did you do with that? What's the dimension of that output actually? Okay, let's just do it on the... Okay, so first you had x. What was the dimension of x? Rm in general. Okay, in this specific case, I had taken m equal to 900. Okay. Then you did this operation. Fine. Tell me the dimensions here. Assume at all, okay, so let's assume that you had the input layer which had 900 pixels, or dimension was 900. Then you had two hidden layers, each of dimension 100, and then the output layer of dimension 4. Okay, let's assume this. Now, can you tell me what is W1? (900 cross 100), right? Is that fine? Okay, so I'm going to call it as M cross D1, where D1 is the number of neurons in the first hidden layer. And I'll have D2 and I'll have K. What is B1? How many biases do you have? One for each neuron in the hidden layer. So that means B1 would be of size R D1. Okay. Now once I computed this was the aggregation. What do I do after that? This is what? This is A1. What do I need to compute after that? H1. Right? What is H1? H1 is G of this. So now I have this guy. I have this layer with me. What do I do to that? To get now from H1, where do I need to go? H2. How do I compute H2? I take this guy. This entire thing, remember, is H1. What do I multiply it by? W. So this was W1, this was W2. So I multiply it by W2 and add B2. Okay. So what's the dimension of this entire guy? This is H1. How many H1s do you have? 100, right? So this is RD1. What's the dimension of W2? D1 cross? Everyone? Last bench? Fine. D1 cross D2? Okay. What's the dimension of B2? What is this entire guy? No. A2. And now to make it H2, what do I have to do? G of this. So this entire guy now is H2. Now from where do I need to go? Output layer. Okay. So what will I do first? Multiply this by W3 and add B3. And then what will I do to that? No, O. For the output layer, we are calling it as the output function. Everyone gets this now? Okay. What are the dimensions of W3? D2 cross K. And what's the dimension of B3? K. One for every neuron. Is that fine? Now everyone gets it how I can write the output as a function of the input. And now just stare at this quantity that you have and see whether it's the same as what we did. Is it the same? Everyone fine with this? Anyone still has doubts? So now my model, instead of being this simple model where I had y is equal to 1 over 1 plus e raised to minus w transpose x, I have chosen a much more complex model. It's actually a very composite function of the x with a lot of non-linearities in between. What do I mean by non-linearities? The sigmoid function. The sigmoid function is a non-linear function, right? And many such sigmoid functions in between. And that's how you finally get y as a function of x. Okay? So now in a deep neural network, I have still assumed that y is a function of x, but now my assumption is much more complex than the simple case of sigmoid. And now you could imagine that in many real world situations, your relation between the y and x is going to be very, very complex, right? For example, even in the oil mining case, it's not going to be that you collect all these parameters, apply a simple linear transformation, and you get the quantity of oil that you will mine from that location, right? It's going to be a very complex combination of all the input factors that you have. And a deep neural network actually allows you to compute such very complex functions of the input. Do you get that? Right? You have done a lot of transformations, and the more transformations that you do, the more number of hidden layers that you add, the more non-linear is your output as a function of the input. Does everyone get that important point? Okay, fine. So now I've written y as a function of the input. What's the next element that I need to tell you? The dash of the model. The parameters of the model. What are the parameters? Which are the weights now? Can you give me the exact parameters? W1, W2, W3, B1, B2, B3. How many in all? No. Each of these is again how many did you have in the original case when we were doing gradient descent? How many parameters did you have? 2. How many do you have now? Many, many more, right? And what the exact number is actually W1 is n cross D1, W2 is D1 cross D2, and W3 is D3 cross K. And similarly, the biases B1, B2, B3 are D1, D2, and K. So if you add up all these numbers, that's the number of parameters that you have, which is for now, it suffices to say that it is much more than 2. Okay? So we did the gradient descent algorithm for 2 parameters. Now we are dealing with many, many more parameters. Okay. But these are the parameters that you have. If I want to write it compactly, this is how I'll write it. And the algorithm, again, is going to be gradient descent, but with something known as backpropagation, and that's what we are going to see today. And the objective function can again be the squared error loss, right? I can look at what are the outputs predicted by the model. I can compare them to the original output, take the squared error difference, and my objective would be to find dashes such that my objective function goes to dash. What do I need to find? The weights and biases such that my objective function goes to minimum, 0 or minimum. Is that fine? Everyone gets this? Okay. So that's again a typical machine learning setup. You have these 5 components, and now you need a learning algorithm which is driven by this objective function to find the parameters. Okay. Now this is again an optimization problem. So let me ask a question which I asked yesterday. This optimization problem is with respect to which parameters? This is an objective. For example, when I said minimize x square, you give me back a value of x, which gives you the minimum value for x square. Now, when I say minimize this loss function, what will you give me back? The w's and the b's. Okay? So the parameters of this objective function are w's and b's. Is that okay? Fine. So what have we done so far? We graduated from this single neuron to a multi-layer network of neurons, right? And we saw that the idea still remains the same. All you're saying is that there's a true function between y and x. I don't know that. I'll assume there is some function. And now I've written that function in the form of a very complex neural network, which is nothing but a composite function of the input, the output expressed as a composite function of the input. And along the way, you had many more parameters as compared to the single sigmoid neuron that you had. And now your goal is to learn all these parameters. But remember a few things which have not changed. My training data has not changed. It's still the same. I've given some x's and some y's. My objective function has also not changed. What has changed is the function, the way of writing output is a function of the input. And because of that complex function, many more parameters. And even my learning algorithm is largely gradient descent, but I just need to do something known as backpropagation, and I'll tell you why I need to do that. Okay?